Hello and welcome back to the Science of Concrete Materials class. This is lecture number 13 of the class. We are still on the cement module of the class, the hydration and microstructure topics. Today's topic is the microstructure properties relationship. We have been studying the hydration, the development of microstructure, and now we want to, like I said, we look at it from a more practical point of view to relate these microstructure characteristics to the properties of the paste or the concrete. As you know, of course, our ultimate goal is to have hardened concrete with certain desirable engineering characteristics, strength, dimensional stability, and durability. These properties, as I just mentioned, are influenced not only by the proportion of the mixture, but also by the properties of the hydrated cement paste, which in turn depend on the microstructural features, meaning the type, amount, and distribution of solids and voids, which we have discussed in details so far. Now that we have appreciation for how the microstructure developed and its makeup, we need to look at the microstructure property relationships of the hydrated cement paste. First, let's look at the strength. It should be noted that the principal source of strength in the solid products of the hydrated cement paste is the existence of the van der Waals forces of attraction. Adhesion between the two solid surfaces can be attributed to these physical forces. The degree of the adhesive action being dependent on the extent and the nature of the surfaces involved. So the small crystals of the calcium silicate hydrate, the calcium sulfoaluminate hydrates, and the hexagonal calcium aluminate hydrates, they possess enormous surface area and adhesive capability. So these hydration products of the Portland cement, tend to adhere strongly not only to each other, but also to low surface area solids, such as the calcium hydroxide or the anhydrous clinker grains that remains within the hydrated cement paste, and also the fine and coarse aggregate particles. So it is a well-known fact that there is an inverse relationship between porosity and strength in solids in general. Strength resides in the solid part of a material, so voids are detrimental to strength. In the hydrated cement paste, the interlayer space with the calcium silicate hydrate structure and the small voids within the influence of the van der Waals forces of attraction are not considered detrimental to strength. So that you have to keep that in mind and go back and look at the some of the slide in the previous lectures to refresh. This is because the stress concentration and subsequent rupture on application of load begin typically at the large capillary voids and the micro cracks that are invariably present within the paste. As stated earlier, the volume of capillary voids in hydrated cement paste depends on the amount of water mixed with the cement at the start of the hydration and the degree of cement hydration. Okay? So when the paste sets, it acquires a stable volume that is approximately I say, equal to the volume of the cement plus the volume of water, assuming that 1 cubic centimeter of cement produces 2 cubic centimeter of hydration products. Powers who is one of the pioneers in the area of cement and concrete research, and thanks to him, made simple calculations to demonstrate the changes in capillary porosity with varying degrees of hydration in cement pastes of different water-cement ratios, as we have seen in the previous lecture. Furthermore, and for normally hydrated Portland cement mortars, Powers showed that there is an exponential relationship of the type you see here on the screen, which is F sub C, or the strength, compressive strength, equals to A times x to the power 3. He showed this inverse relationship between the compressive strength, Fc, and the solid to space ratio, denoted as x. We have seen this in the previous lectures. A is a constant equal to 34,000 psi or 234 MPa, depending which units you're using. So this is the exponential relationship devised by Powers. So assuming a given degree of hydration, such as 25%, 50, 75, up to 100%, it is possible to calculate the effect of increasing the water cement ratio first on the porosity, and subsequently on the strength by using Powers' formula. The results are plotted, as you can see here in this curve. This is the relationship between the capillary porosity and the strength. Of course, here is the permeability. We will talk about it in a bit. It is clear to see how strength decreases with the increase in porosity. I will talk about of course, porosity increase with the increase in water cement ratio. We mentioned this several times, and I will talk about this in a bit. Okay, the next property we will talk about is the dimensional stability of the paste or the concrete. So it is known, saturated hydrated cement paste is not dimensionally stable. So as long as it is held at 100% relative humidity, practically no dimensional change will occur. Okay, when exposed to environmental humidity, which normally is much lower than 100%, the material begins to lose water and shrink eventually. How the water loss from the saturated hydrated paste is related to relative humidity on one hand and to the drying shrinkage on the other is described by the work by Le Hermet. I hope I pronounced that correctly, and this is shown on the next slide. I will talk about it. So as soon as the relative humidity drops below 100%, the free water in the large cavities, meaning cavities larger than 50 nanometer, begins to escape to the environment. Here's the curves I just talked about. Take a note on these curves, and showing the relationship between the relative humidity and the loss of water. Okay, and this one showing the loss of water and shrinkage. Okay, so because the free water is not attached to the microstructure of the hydration products by any physical or chemical bonds, its loss would not be accompanied by shrinkage. This is shown by the curve AB on this figure here. If you want to go back to the previous slide, but I'm showing this here for reference again. Okay. So a saturated hydrated paste exposed to slightly less than 100% relative humidity can lose considerable amount of water, of total evaporable water, before undergoing shrinkage. As you can see here, there is loss of water, but the shrinkage is not considerable. When most of the free water has been lost, it is, found on continued drying that further loss of water results in considerable shrinkage. This is represented or shown by the curve BC, as you can see here. The relative humidity drops, then we see a considerable amount of water lost. Okay, and again, the shrinkage, you could see the shrinkage here, how it happened. Of course, this is for old, this is for young. The difference is understood, but this just shows you the effect of relative humidity on the evaporable water. Okay, so this basically the curve BC is attributed mainly to the loss of adsorbed water and the water held in the capillaries. Okay. As you can see here, I talked about this schematic several times before, and we talked about, here's the bonding we talked about, and here we talked about the porosity, the type of pores, and what the effect of the loss of this type of water, whether it causes shrinkage or not. Okay, so it has been suggested that, when confined to narrow spaces between two solid surfaces, the adsorbed water causes disjoining pressure. The removal of the adsorbed water reduces the disjoining pressure and brings about shrinkage, of the system. The interlayer water present as monomolecular water film, within the calcium silicate hydrate structure, can also be removed by severe drying conditions. All right. This is because the closer contact of the interlayer water with the solid surface and the difficulty of the transport path through the capillary network usually call for a stronger driver force, because the water in small capillaries between 50 to 50 nanometer exerts hydrostatic tension. Its removal tends to induce compressive stress on the solid walls of the capillary pore, by this, causing contraction in the system. You have also to note that the mechanisms that are responsible for drying shrinkage are also responsible for creep of the hydrated cement paste. In the case of creep, a sustained external stress becomes the driving force for the removal of the physically adsorbed water and the water held in small capillaries. So creep strain can occur even at 100% relative humidity, because the driving force is not the removal of the water by the change in the relative humidity. And again, you could refer back again to this slide here and what I talked about before, just for more information. Okay, so let's talk now about durability and how it's impacted. The hydrated cement paste is alkaline, as we mentioned. So exposure to acidic waters is detrimental to the material. Under these conditions, impermeability or water tightness becomes a primary factor in determining the durability. The impermeability of hydrated cement paste is a highly prized characteristic, because it is assumed that an impermeable hydrated cement paste would result in an impermeable concrete. Of course, you know, the aggregate in concrete is generally assumed to be impermeable. So permeability is defined as the ease with which a fluid under pressure can flow through a solid. It should be obvious that the size and continuity of the pores in the microstructure of the solid would determine its permeability. Again, back to these curves I've shown earlier. Strength and permeability of the hydrated cement paste are two sides of the same coin, in the sense that both are closely related to the capillary porosity. Just keep mentioning this term, the capillary porosity. You have to go back to that schematic and look at the type of pores and how they contribute to the properties of the concrete. You know, they're related to the capillary porosity or the solid space ratio. This is evident from the permeability curve shown here. Okay, which is based on the experimentally determined values of the permeability by powers. Okay, as we said, as porosity increases, so does the permeability coefficient. As you can see, this is the permeability coefficient here on this axis. As capillary porosity increases, permeability increases. Look at the exponential relationship. And the same we said with strength, we talked about strength decreases with the increase in the capillary porosity. The exponential relationship between the permeability and porosity, as we shown in the figure below, can be understood from the influence of the various pore types exert on permeability. As hydration proceeds, the void space between the originally discrete cement particles gradually begins to fill up with the hydration products. So it, as has been shown and explained previously, that the water cement ratio, which is the original capillary space between the cement particles, and the degree of hydration determine the total capillary porosity, which decreases with the decrease in water cement ratio and or the increase in degree of hydration. If you remember here, we talked about, when we talked about the volume changes, I have shown schematics similar to this, and we have seen how the effect of the hydration and the water cement ratio on the capillary porosity. And also it is evident here, as with the increase for all degrees of hydration, the increase in water cement ratio, increase going down, the capillary porosity increases, and with the increase in hydration going left, with the increase in hydration, the capillary porosity, of course, decreases. The mercury intrusion porosimetric studies, we talked about this before, and I'm showing here the slides, the figures. The intrusion porosimetric studies on the cement paste hydrated with different water cement ratios and various ages, again, as I said on these two graphs. It demonstrates that the decrease in the total capillary porosity was associated with the reduction of the large pores in the hydrated cement paste. Look at this. Basically, the decrease in the large pores. Go back. From the data, given in the figure, it is obvious that the coefficient of permeability registered an exponential drop when the fraction of the capillary pores was reduced from 0.4 to 0.3. This is, the range of the capillary porosity therefore seems to correspond to the point when both the volume and size of the capillary pores in hydrated cement paste are reduced such that the interconnections between them no longer exist. And go back and when we talked about the definition of permeability and what constitutes a permeable versus a porous solid structure, it's the connection of the pores. And what I just talked about, look at it here. This is a 0.4 fraction, and this is 0.3. Look at the drop. It's severe. So basically, I mean, in reducing the water cement ratio can go a long way, and the increased hydration as well can go a long way in reducing the capillary porosity. So as a result, the permeability of the hydrated cement paste may be on the order of 10 to the power 6 times less than that of a young paste. That's how much full hydration do for us. Powers showed that even with on a complete hydration, 0.6 water cement ratio paste can become as impermeable as a dense rock such as basalt or marble. So complete hydration is key, and that means in practical terms curing and water loss prevention, after pouring the concrete. Also note that the porosities represented by the calcium silicate hydrate, interlayer space, and small capillaries do not contribute to the permeability of hydrated cement paste. On the contrary, with increasing degree of hydration, although there is a considerable increase in the volume of pores due to the calcium silicate hydrate interlayer space and small capillaries, the permeability is greatly reduced. So that means which pores contribute to the permeability and which do not. In hydrated cement paste, there is a direct relationship between the permeability and the volume of pores larger than 100 nanometer cube. This is probably because the pore system, comprised mainly of small pores, tend to become discontinuous. So again, the continuity of the pores is what constitutes permeability. Okay, so let's summarize. Permeability is dependent on the size and connectivity of the capillary pores. Permeability is not dependent on gel porosity. In reasonable range of water cement ratios and near full hydration, the connected fraction of the pores almost non-existent. In well-hydrated cement paste, the permeability is roughly 10 to the power 6 times less than young paste. So again, reducing water cement ratio and increased hydration reduce permeability, refinement of the microstructure, and reducing pore size is an objective of ours to have better performing, more durable concrete. So just with that, you have, I will mention a few points. Again, water cement ratio controls porosity of the hardened cement paste. High quality control on concrete consists of low water cement ratio and permeability. A low water cement ratio and adequate curing are key elements in concrete technology. So remember, keep that in mind, please. A particularly low water cement ratio can be achieved in mixes using the high range water reducers and very fine pozzolans such as silica fumes. We will talk about those when we talk about chemical and mineral admixtures. I'm just mentioning these here since we are on the subject of refining the microstructure. These mixtures typically achieve compressive strength levels in the range of 50 to 130 MPa. by having low water cement ratio, good curing, and using water reducers and pozzolans. Also, high strength and low permeability concrete can be achieved. Low water cement ratio, proper mix proportioning, use of super plasticizers, use of pozzolans, and high degree of hydration, good curing, we can achieve high strength, low permeability concrete. Okay. This is the end of lecture number 13, and basically after this we have 2 more topics to cover in the cement module, which is the interfacial transition zone, the ITZ, which really more on we touch in that lecture more about the microstructure of the concrete rather than the paste alone. And also we have a remaining topic, which is the remaining types of the cements, if you remember. Those 2 topics, after that we close this module and we will move on to the next topic. So thank you for watching, and I hope I'll see you next time. Thank you.